Hello, everyone. In this video, I'm going to be going over problem 12 of chapter 11 in the Fundamentals of Mass and Heat Transfer textbook. So, chapter 11 is all about heat exchangers. Problem 12 says that a shell and tube exchanger, two shells for two passes, is used to heat 10,000 kilograms per hour of pressurized water from 35 to 120 degrees C, with 5,000 kilograms per hour pressurized water entering the exchanger at 300 degrees C if the overall heat transfer coefficient is 1,500 watts per meter squared. Determine the required heat exchanger area. So in order to solve this problem, first thing I did is I wrote down all the values. In order, the next, consulting table A6, for the cold temperatures, I decided to evaluate them at their average of 350 Kelvin, which is just 35 plus 120 over 2, and then just plus 273 from there to get a specific heat of 4,195 joules per kilogram Kelvin. And then for the warm flow, I decided to assume a temperature of 150 degrees C, which would give us an average of 500 Kelvin and a specific heat of 4,660 joules per kilogram Kelvin. Uh, why why I had to assume? I'll go over that in a second. So first thing I decided to do, my first thought was to try and evaluate this using the log mean temperature difference. And since we are given 3 out of the 4 required temperatures, I decided to use a mass balance in order to find the outlet temperature of the hot pressurized water. So, Q is equal to m dot C specific heat times temperature difference of the cold, which is equal to the m dot times C of hot times the temperature difference of the hot. Using this, I got a temperature of about 147 degrees C, which is very close to my assumption, meaning that I chose a good temperature to assume. In these cases, the best process, if you don't know one of the temperatures, is to just assume a outlet temperature, go through it, see what you actually get, and then if it's not super close to your assumed temperature, I'd say about like, I don't know, arbitrarily for me, I'd say about 5 degrees off or something. Then you just use that new temperature that you got as the basis for the properties you use, run through the balance again until you get an adequate temperature, I'd say. And so using uh so since we were able to confirm that 150 is a good temperature, we can then find the heat flow from the hot to the cold. We could just use the cold for that since we know for a fact what all the values are, which will give us about 3.5 times 10 to the 9 joules per hour Kelvin. And converting all that into, standard watts will give us 9.905 times 10 to the 5 watts, which is just joules per second. And so this block right here, decided I just started doing anyway. Uh, this has to do with the efficiency NTU method, having the C of cold, C of hot, the critical C, uh, because after I'd done the balance, I thought to myself that NT that unfortunately log mean temperature difference just quite isn't adequate for a shell and tube exchanger. However, I still decide to go through both methods. So first, I'm going to talk about the log mean temperature difference. Using this, Q is equal to the total heat transfer coefficient U, which we were given, times the surface area times the log mean temperature difference. So normally, a log mean temperature difference is supposed to have normally it's supposed to have a fudging factor in the cases uh, where you have more complicated flows than counterflow. Uh, this is this is something that changes it so slightly. I probably, if I had included the fudge factor, I'd actually get something a bit closer to the actual surface area than I did. Uh, so, just to go over it, the delta temperature of the log mean is equal to delta T2 minus delta T1 over ln T2 over T1. In counterflow, which shell and tube heat exchanger is most closest to, delta T1 is equal to the hot input minus the cold output temperature, and T2 is equal to the hot outlet temperature minus the cold inlet temperature. Plugging all that in gives a delta T log mean equal to 145.081 degrees or Kelvin. Uh, so as I said, I'm gonna pull up chapter 11 in the textbook. I'm gonna go all the way up. Uh, yeah, special operation conditions. Uh, talks about what we see here. However, neither of these graphs used for conditions really properly talk about or mention exactly what's happening in this heat exchanger. This one, delta T1, delta T2 is equal. In these ones, you have converging temperatures. Uh, so as I mentioned, in more complicated uh, heat exchanger situations, you would need a fudging factor in order to use log mean temperature difference. What this value f would be, you would have to consult a table in order to find it. And what the table looks like is going to be different depending on what exactly the heat exchanger looks with. So, so even though I forgot the fudging factor, I got 4.55 meters squared for the surface area. However, as I mentioned, because this is a more complicated heat exchanger, using the efficiency NTU method is far better in this instance. So, so since we have the CH and the CR, first thing you do in in cases like this is you want to find the Q max. Q max is equal to the C min, which in this instance is the C of the hot, uh, times the times the inlet temperature difference, which will give us a maximum power of 1.75 times 10 to the 6 watts. We can then find the efficiency by dividing the energy that we found over the maximum energy, giving us an efficiency of 0.577. Now, this is where the equations get complicated. So, if you look at the textbook in chapter 11, I have currently brought up table 11.3. This this is the this table has to deal with heat exchanger effectiveness relations between with what exactly type of heat exchanger you are using. So here we can see a shell and tube, and we and it says that the efficiency is equal to equation 11.31a, where specifically n is equal to 2 because this is a shell and tube with two shell passes. Now, if now now equation 11.31a isn't all that useful, uh, but if we scroll down to table 11.4, this is the one that has the more useful equations. Specifically, equation 11.30b is very useful, as well as equations 11.31b, c, and d. So it tells us that the NTU is equal to the n times NTU of 1. However, using an equation 11.30b tells us what NTU of 1 is equal to. If you combine those equations, you'll get this complicated equation right here, but that's just adding the n, as you can see in the NTU, to equation 11.30b. However, as you can see in this equation, you're going to need the value E, which the value E you can find so long as you have the effectiveness 1 value. Effectiveness 1 needs the value F, and here we can see that the value of F is in terms of the effectiveness, the efficiency times the critical thermal mass, or CR, and the number of passes. So moving backwards from F, we find that F is equal to 1.27. We can then find the efficiency 1 value, which is equal to 0.376. We can then find E now, which is equal to 3.29. And then once we have the E, we can plug that into the NTU equation, which will result in an NTU equal to 1.10. From here, we can finally plug NTU into an equation that will give us the surface energy, which is that NTU is equal to U times A over C min, which is equation 11.24 in the textbook. Here, it's just solving for A, which will give us a final surface which will give us a final more accurate surface area of 4.75 meters squared. So just to summarize all this, when dealing with shell and tube heat exchangers and more complicated heat exchangers than just parallel and counterflow, it might be better to just use the NTU method. So that's all for this video. I hope that it was very helpful for those who are, and I hope that other videos on this channel will serve you just as well as this one. Have a good day, and bye.